All right, let's get started. Let's finish the theory building by proving finally that the two way of defining entropy, the way we define it using this function, explicit definition, which is, let me write it down, the entropy, so the explicit definition of the entropy is of a random variable is the sum over, if let's say x is defined over some set, takes value over some set A. Then it's the sum over the probability of x log base 2, 1 over probability of x. And recall this px is just the probability that x takes value little x. And we have the axiomatic definition. We're going to show that these two is equivalent. So we need to do two directions. One, let's start with the easier direction that this explicit definition, so this choice of entropy function satisfies all the axioms. Let's do this direction. So we have many axioms that we defined. So there's a question asking if the entropy can be defined for a random variable over defined over infinite sets. So throughout this course, we will always be talking about this discrete random variable most of the time. There are some version of it for infinite one. We will not be talking about those. So maybe in the notes, I will add some further readings regarding further extensions. Okay. So coming back here, so everything is finite. The set A over which we're going to take the values, this random variable is finite. So let's first prove that this choice of entropy, explicit definition, satisfies all axioms. Most of the axioms are very trivial. The only two non-trivial one is maximality and additivity. So that's only going to prove those two. Proposition 1, proposition before that, let's recall, we need to recall useful inequality, which is Jensen's inequality. Jensen's inequality says that if we have a random variable, x, and if we have a convex function, or convex, respectively, then we have the expectation, which I want to write it, of x is greater than expectation of, let me write it like this. So maybe I'll write in red. So if it's concave, we have the other way. The way to remember this inequality is just by picture. So concave is the opposite of convex. So let's just remember convex. By picture, how do we remember it? Well, if we have a convex function. So it looks like this. This is our f. Let's first plot the left-hand side. What is f of expectation of x? So if, let's say, x takes these two values, then expectation of x, f of the expectation of x is here. This is f of expectation of x, right? But what is expectation of fx? This is fx. So expectation of fx is here. Which is larger. Okay. So maximality basically follows from Jensen's inequality. Let's prove that if we have if we have entropy defined in this way, then it satisfies maximality. So let's give this a name. Let's say heart. Let hx defined as in this explicit definition, then it satisfies maximality, meaning it's maximized over uniform distribution. So proof. All we need to know is this log function is a concave function. It looks something like this, right? Log. So we can use Jensen's inequality. This form we have as fx equal to log x is concave. Jensen's inequality implies we have h of x, which by definition is this guy, px log 1 over px, is at most log sum over px 1 over px. Okay. So we apply this one with f being log x. This is precisely f, wait, expectation of x. Am I doing it right? I think I write this in the wrong way, no? F, this is at most. Right, no one correct me here. You see, this is the opposite way. I get confused. So this is a convex function. This point in the x-axis, expectation of x. Then on the curve, that's f of value of that. So this is correct. This is also correct. This is f value, take its expectation. This is also correct. So this side is larger than this side. It should be this way. That means we should have this way. Okay, now it's correct. Now you see, this side is precisely this side. We have f function, it's log. This is expectation of x. So the random variable takes value 1 over px with probability x. Here, it's expectation of fx. So fx, f is log, x takes value 1 over px with probability fx. All right? Good. And here, inside is nothing but size of a. So it equals to log of size of a. With equality, when all px are equal, which is x is uniformly distributed over A. Finishing is the proof. Okay. Maximality. Now let's prove additivity. Additivity says what? Remember, h of xy equals to h of x. So we're given the information in x. Now, given information of x already, what do we get additionally from y? This is additivity. Let's prove that if hx defined like that, it also satisfies the additivity. And additivity satisfy these two. So this is first part, second part. Okay. So we need to show hxy equals to h of x plus h of y given x. So let's first write out the definition of joint entropy and conditional entropy. That everything will follow from definition basically, and some calculation. To write things in a more concise way, let's say we have y taking value. Y is a random variable defined over a set B, where we're going to write Q sub A, Q sub B to denote the probability that y takes value little b. Okay, and I'm going to write PAB for the probability that x takes value little a, y takes value little b. And we're going to write conditional probability also in the short form like that. This, as you might guess, is the probability that y takes value b given x takes value a. With this short form, let's recall the definition of hxy. Then hxy equals to nothing but the sum over a in A, b in B, PAB log 1 over PAB, using the explicit definition. Now, let's just observe some trivial inequality, a trivial property from these three. What is PAB? PAB equals to the probability that x equals to A times probability that y equals to B given x equals to A. This is the join event, right? One happens, conditional one happens, the other happens, which is nothing but PA times QB given A. So we can then further rewrite this joint entropy. So we're going to replace PAB here by this guy. So it's going to be equals to sum over A in A, B in B, PAB log. So let me write one more step. AB, PAB log 1 over PA dot QB given A, right? But the log of this product is basically log of 1 over PA plus log of 1 over QB given A, this guy. So we can write this as log of 1 over PA plus log of 1 over Q. No problem. Let's look at each term. let's first look at this term. So this term, for the first term, let's split A and B. Look at the first term, PAB log 1 over PA. Okay, that's the first term. Well, this is independent of B, so let's look at what is this guy. That's precisely probability that A happen, X equal to A, Y equal to B, sum over all B. That's the probability, that's basically PA. So this equals to sum over A in A, PA, log 1 over PA. This, by our definition, is H of X. So the first term is entropy of X. We just need to prove that the second term is the conditional entropy Y given X. So left to show second term equals to this guy. Okay, so let's first look at what this guy looks like by definition of conditional entropy. Is the sum over all A in A PA entropy of Y given X equal to A. This is the definition of conditional entropy. So let's look at the second term. Does it look like that? The second term equals to, write it out, A in A, B in B, PAB log 1 over QB given A. That's the second term. So what we're going to do now is we're going to multiply something. Right. Again, let's use this guy. PAB equals to PA times Q of B given A. So let's replace this. Okay. That means let's split the sum A and B again. Equals to sum over A in A. Little pa is independent of B, so we can write in the front. Everything depends on B. Put it in the back. So B given A log 1 over Q B given A. Now let's look at what's inside this sum. This is exactly this by definition, by the hard definition. It's the sum over A in A, PA, conditional entropy X equal to A, which is exactly what we want. Any question? We finished proving one direction, that the explicit definition satisfies all axioms. The other axioms are trivial. I will leave it as exercise, leave them. Now let's prove the other direction. Given this set of axioms, we're going to show that there's no other way than defining the entropy as this. This is the only way. It basically follows from normalization and invariance. Let's see how it goes. Now we show the axioms implies the definition. It's a unique way. So lemma. For that, let's first prove a lemma, which we've sort of used it before. We assume it as a black box. That's when when X is uniformly distributed, the entropy is log of the size of the range. So X is a random variable, uniformly distributed over some set A, finite. Then the entropy of X equals to log of size of A. This can be easily proved using this hard definition, but we're going to prove it using axiom. All right. First, let's prove it for powers of when A is of size power of 2. That's quite easy. Proof. So let A to be of size n and consider the special case when n is a power of 2. In this case, as I said, it follows from normalization and invariance. We know by normalization, if we have y uniformly distributed over a set of size 2, then the entropy of y is 1. This is normalization, the axiom. Now we have a set A, X, uniformly distributed a set which is power of 2. What do? We can just take IID copy of Y and build a one-to-one correspondence to X. They will have the same distribution. In other words, we're going to take, this implies if we let Y1 to YK be IID copies of Y, then remember independence implies the entropy of Y1 YK equals to K times the entropy of Y, which is K. Okay? But what is this guy? This guy notes that Y1, this joint random vector, distribute randomly over a set of size 2 to the k. So that means this random vector and x, because x is randomly distributed over also a set of size 2 to the k, has the same distribution. So by invariance, entropy of x is the same as entropy of y1 yk, which equals to k. And that's log of a. For the special case that a is of size 2 to the k. For the general case, basically, we're going to approximate a by powers of 2. So now consider general case. Now, for general n, we're going to approximate it by power of 2. First, let's define delta to be the error, which is h. We want to prove x is the same as log n, right? So let's let delta to be the difference. And our goal is to show that delta equals to 0. That's our goal, right? That's our goal. Okay. How do we prove it? Well, again, we take IID copies of x. So if you take IID copies x1 to the top, xr for some r of x, what do we get? By independence, we have the joint entropy of this equals to r times h of x. no problem. But what is this guy? Remember, this guy is uniformly distributed over a set uniformly distributed over a set of size n to the r, right? Each guy is over a set of size n, r copy n to the r because of independence. Remember, one of the previous lemma, we say that if x is uniformly distributed over A, y is uniformly distributed over B, and if A is less than equal to B, then the entropy of x is less than entropy of y, right? Monotonicity. Now, that means if we can choose k to sandwich n to the r, let's say you pick k so that n to the r is sandwiched between these two numbers. We have, by the previous lemma, monotonicity. That entropy of this guy, which is uniformly distributed over this set, is at most the entropy of the random variable uniformly distributed over a set of this size. But we proved for power of 2, such entropy is k plus 1, right? And the special case, n equals 2 to the k above, we get that r times entropy of x, which is this guy, is at most k plus 1, at least k. All right. Okay, so let's divide r on both sides. This implies entropy of x is at most k plus 1 over r, at least k over r. Subtract log n on both sides. You have k over r minus log n is at most. Subtract log n on both sides, we get delta. The error term. Okay, by definition of k, this is non-negative. Yeah, this is non-positive. Definition of k implies this guy is greater or equal than 0. This guy is less than or equal to 0. What does it mean? That means delta is sandwiched between these two numbers, which has difference r1 over r. This implies absolute value of delta is at most 1 over r. Okay. Since the choice of r was arbitrary, we can take arbitrary number of RAD copies of x. That means delta must be 0, as desired. Any question? Okay. So the last lemma in the theory building, saying that x is a random variable defined over some finite set A, if x satisfies all 6 Shannon-Khinchin axioms, then there's no other way but to define the entropy as what we wrote above. With all this preparation, the proof of this is not so hard. Proof. By continuity, we can assume that the atom probability of X is rational. By continuity, we may assume PA equals to some natural number MA over some common denominator N, or some MA in N for every A in A. Okay. We need to make use of this different view of this association of X, which takes rational atom probability to the uniform distribution over N. Remember this construction. So let's recall in previous lecture, if we let N U to be a random variable uniformly distributed over N, and X prime, and what we do is we're going to partition N into union of VA, A in A, remember? And VA is of size PA times N, which is MA. Then X prime, we define X prime to be A if U is in VA. In this way, X prime and X are identically distributed. This is recall from before. Okay. In other words, their entropy are the same by invariance. And also, because X prime is determined by U, by dependence, one of these lemma, their joint entropy is the same as just telling me U. If you tell me U, I know everything about X prime. So these two are the same. And also, another property is the random variable U, if given that X prime is A, this is uniformly distributed over the set VA. All right. Using this property, now what do? We can prove now that, so, okay, let's first compute this guy. Let's first compute conditional entropy of U given X prime. This guy equals to, by definition of conditional entropy, the sum over A in A, the probability that X prime takes value A, times the conditional entropy of U given that X prime is A. Okay. Now the trick is, look, what's this random variable? This random variable is uniformly distributed over VA. By the previous lemma we just showed, when you take a random variable uniformly distributed over set, its entropy equals to log of the size of that set. So this guy equals to log of VA. VA is this guy. Okay. So this equals to sum over A in A, PA because x and x prime are identically distributed, times log of PA times n. Good. So now we can write, let's compute what's the entropy of x. The entropy of x is the same as entropy of x prime. They are identically distributed. By additivity, this equals to h of x prime u minus h of u given x prime. We've computed this guy here. But what is this? Remember, the joint entropy is the same as HU. So let's replace this by HU minus this guy that we computed above, PA log PA times N. What is the entropy of U? Remember, U is uniformly distributed over N. So the entropy of U is log N. Is equals to log N minus, let's split this log as sum, A in A, PA log PA plus log N. We are done here basically. The rest is computation. You see, if you split these two terms, what's the second term? Second term log N is independent of A. The sum of this is 1. So this is basically log N. Cancel with this log N. So we are left with this term, move minus in here. That's basically this guy, which is precisely the hard definition of entropy. So this, let me write one more step, is equals to sum of A in A, PA log 1 over PA. Okay. Good. Let's summarize. That finishes the theory building for some basic properties of entropy. Let's summarize what we've seen so far. I'm going to do the summary in terms of a more general conditional version of the basic property. Everything we've proved so far works if you condition on something. So, summary of properties. Properties, yes. So in below, we're gonna have x, y, z, and those xi are random variables. And E is some event. We're gonna condition on. F is some deterministic function. We're gonna write range of x given E to be the set of values that the conditional random variable x, given that the event E occurs, takes. Okay. With positive probability. Conditioning on E. Yeah, no, just like this. Okay, then maximality. Maximality says random variable entropy is maximized when it's uniformly distributed. Works also for the conditional version. It says that the conditional entropy of X, given that some event E occurs, is at most when it's uniformly distributed. And we know when it's uniformly distributed, it has log of the size of the range. Okay. With equality if and only if it's this conditional random variable distribute uniformly at random over this set. Now we have chain rule. Chain rule is okay. Chain rule is in a conditional way. H of x1 dot xn condition on some random variable x y is the same as sum over I in n. Let's review the information one by one. First, review x1, then we review x2 given x1, so on and so forth. Okay. Oops. This is the normal chain rule. Now, it also works if we condition additionally some y. No problem. Monotonicity. Monotonicity. I think I call it dependence. Let me change the name. I may change this name later. Dependence. What does this say? This says that if S equals to Fy, what this means is that X is determined by Y because F is deterministic. If X is determined by Y, then the information, the surprise we get from X is no more than the surprise we get from Y. Then H of X is at most H of Y. Similarly, if more generally, if X is determined by Y and Z, then we have entropy of X given Z is at most the entropy of Y given Z. How we read these is that because given Z, if Z is fixed, X is determined by Y. Right? So given Z, X is determined by Y, then we get the same thing. It's a conditional version of this. Good. There's another one, which is if Y equals to F of Z, then we have H of X given Z is at most H of X given Y. What does this mean? Also intuitive. Because Y is determined by Z. So Z has more information. If you review more information at the beginning, right? Z has more information than Y at the beginning, then the additional information you get from X is going to be less than the additional information you get here given Y. So what this means informally is that if we review less front y instead of z, so it's less, then we get more information later. Dropping the conditioning also works here in the conditional setting. This says that conditioning more is only going to decrease the entropy. So we can drop 1 to increase the entropy. If you know less at the beginning, you're going to get more from Z. Subadditivity. In the conditional setting, is saying h of x1 xn given y is at most sum of h of xi given y. Okay, equality holds when each xi, they are conditionally independent, conditionally independent given y. Now, also Shearer's lemma, it works in the conditional setting. This is an important lemma. We're gonna now see applications. Let's recall this lemma. In the conditional setting, it says that, well, given some random subset of the indices of your random vector with such that each index in the vector lies in this random set with probability at least mu. There's a lower bound on the probability that each index is covered for each I in n. Then the entropy of X, joint entropy, given Y, this is the conditional version, is at most 1 over mu expectation over this random set F, conditional expectation of XF given Y. So everything's the same, just with this conditional version. And recall, this is what? This is basically the random vector xi, but you only look at the coordinate that lies in F. Okay. Now let's look at, this finishes all the theories I want to talk about for entropy. Any questions so far? We've seen some applications already, like estimating the volume of the Hamming ball, and also a quick application of Shearer's lemma on this Loomis-Whitney inequality for estimating the volume of a convex body by through the volume of its projection. Now let's look at some graph theory application. The first one it's about triangle maximization. It's a special case of Kruskal-Katona. So applications. So the theory part is a little bit dry. I think at the first touch, it's enough to understand the proof line by line, and all you need to do is to remember this property. So you can forget about the proof of this basic property. Just remember what it says. That's enough to understand all these applications that we have. So memorizing this is quite intuitive. You using the fact that informally entropy measures the amount of information that a random variable carries, it's easy to memorize all these facts. Using it as black box, we can do all these applications already. So let's see some graph theory one, triangle maximization. Maximization. This is a special case of Kruskal-Katona theorem, which is a cornerstone theorem in extremal set theory. I believe we mentioned it last semester. But here in this special case, what he says is that if we given the number of edges a graph can have, then what's the maximum number of triangles this graph can have? So the setup is we have a graph given the number of edges. We want to maximize the number of triangles. Okay. This is the setup. Let's say number of edges is m. What's the maximum number of triangle? Before doing it, again, it's good to draw some very simple cases to get some intuition. Well, if let's say we have 3 edges, very simple. You have 3 edges. The worst case is you spread them out like this. You don't get any triangle. So if you want to get a triangle, you put them together. You get 1 triangle. Okay, that's trivial. Now, if you have, let's say 10 edges, 6. So basically, if you have a bunch of edges, let's say 6 edges, if you group them up into clique, you can get many, many triangles. Versus if you spread them out, right? This is 2 extreme case. They are very spread out. They are very clustered. And obviously, the cluster case has more triangles than the spread out case. Intuitively, one will guess, is it true if we pack the edges as compact as possible in this clique manner, do we always maximize the number of triangles? And that turns out to be the case. So the intuition is that number of triangles is maximized when edges are clustered together. Into a clique, right? So if we conjecture that the clique is true, let's work out some computation. We have m, the number of edges, let's say it equals to k choose 2. Then the best we can do is pack into a clique of size k. Then the number of triangles in this case is k choose 3, right? So what is k choose 3? Roughly k cubed over 6. What is k? Well, from here, we know that k is roughly square root 2m. Okay, so that means this is roughly 1 over 6, 2m. to the power 3/2. So asymptotically, is it true that when we're given the number of edges is m, x maximized over clique, meaning that asymptotically is at most this guy? And that turns out is true. This is what we're going to prove. Theorem. An m-edge graph has at most 2m to the power 3/2 over 6 many triangles. Okay. Good. Remember how we mentioned at the beginning of in the first week that if we want to give an upper bound on the cardinality of a set, in this case, this set is the set of triangles in the graph with given number of edges. One way of doing this is say we associate the cardinality to the entropy of the random variable which defined over this set. So if we define the random variable to be uniformly drawn from all triangles, then the entropy of this is log of basically the number of triangles. All we need to prove is that to give an upper bound on the entropy, which is log of this guy. Okay, then hopefully additivity or Shira's lemma will help. And that's how exactly we're going to do it. So, but instead of drawing triangles uniform random over all triangles, we're going to do things in the labeled way. So consider let T to be the set of all labeled triangles in G. So what does it mean? Think of G is itself is labeled, the vertices. Okay, there's a question in the chat. Let me see. So the question says, given some positive constant P and the bipartite graph H, what is the maximum of H density among all G with H density P? Okay. Minimum is the Sidorenko's conjecture. Maximum maximum. Bipartite version. I have to think a little bit on top of my head. I can't answer immediately. So maybe play with some simple example. I will try C4 definitely. So given H density P, maximum for C4, let's play with, let's say, dense graph, P equal to 1/2. Among all graphs with density 1/2, which one maximize C4 density? The obvious thing I would try is you compare clique, which has an isolated vertices that has edge density 1/2, and then you compare complete bipartite graph that has edge density 1/2. And then you take, yeah, right, these two, which are likely candidates. Just play around some obvious choices and see. So I'm starting with some small examples. Good. So let T to be the set of all labeled triangles. What does it mean, labeled triangles? So each triangle come with some G is defined over some vertex set. We think of this vertex set is labeled. Okay. So here 1, 3, 4, even though it's one triangle in the set of all triangles, but in the label setting, it counts as 1, 3, 4 is a triangle. This is also a labeled triangle. This is also a labeled triangle. There are 6 ways, 6 labeled triangle from permutation of these vertices from the single triangle. So the size of T is 6 times the number of triangles in G. So cardinality of T, let's call it little t, is 6 times the number of triangles in G. In this case, we need to show T is at most 6 times this guy, which is 2m to the power 3/2, which is the same as log T base 2 is at most 3/2 times log of 2m. All right. Now, what is log T? As I said, log T is basically the entropy if a uniform random choose a label triangle from T. So define X to be uniform random chosen from all label triangle. And let's write X in terms of random vector x1, 2, 3 to indicate its vertices. This is vertices of X. Okay, you can fix a generic labeled, yes. Okay. Then we know by uniformity, by maximality, we know log T is entropy of X. So now this is our goal. Yeah. Good. Well, we're going to use I wrote it as a vector form. The only tool we have at hand is Schur's lemma. And Schur's lemma says we're going to choose a random set of, which is a random subset over indices. Indices of the vector is set 3. What's the obvious set we're going to choose? Well, the triangle comes in the form of edges, right? It has 3 edges. And the bound we want to prove here is the number of edges. So the obvious thing to choose is, okay, let's choose random pair over this index set of size 3. So we're going to try let this random set of indices to subset of indices to be uniformly distributed over pairs of coordinates. This implies that for every I in 3, the probability that I in F obviously is 2/3. Then Schur's lemma implies that the entropy of X is at most reciprocal of this probability, 2/3. So we have 3/2 times the expectation over F H of XF. But what is this guy? Look. Let's look at this guy. H, note that XF takes value what? F is a pair of coordinates. You choose a pair of coordinates. When you fix to a coordinate, this is xf, right? If let's say f is 2, 3. You have a labeled triangle, which is x. You choose 2 vertices in here. This is a labeled edge. So xf takes value over all labeled edges in G. The number of labeled edges is 2 times the number of edges because you have an edge, you can flip it in 2 different ways, right? So which has size? This implies that the entropy of xf by maximality is at most log 2m. Maximality. This is true for any f, right? So it's true for over expectation as well, and we are done. This implies that hx is at most 3/2 times log 2m as desired. Any question? This is the simplest case application of Seurat's lemma. Let's summarize the idea. Basically, the first thing you should try when you try entropy is you estimate some cardinality of some sets, right? Then you uniform random choose a element from these sets you want to estimate. You associate its cardinality, well, the log of that, to the entropy of these. Now you say, okay, the entropy of these, can we somehow use Seurat's lemma in this case by choosing random pair to associate to the bound we want to prove? So that's all I want to talk about for the application on Kruskal-Katona. I'm going to point out to 2 further readings if you're interested in this direction. One is a very recent paper titled Kruskal-Katona type problems via the entropy method. This is by Yingwei Zhao and Ang Shengyu. That's one. They prove the full Kruskal-Katona basically through entropy method. Here we prove the simplest case, the triangle maximization case. There's another one. In Kruskal-Katona, we can think of we are given the number of edges. But the number of edges is nothing but the little L1 norm of the degree sequence. Okay. So another paper, recent paper, is when we given, instead of L1 norm, given little LP norm of degree sequence. All right, this paper probably will appear very soon on arXiv by Zhao Dong. Jinsen and Mingyue Yang. They also use entropy method. So if you're interested, you can read these two. The next, we have time for one more application. It's another type of problem similar to this Erdős-Corrado type problem we've seen in extremal set theory. It's the triangle intersecting family. Triangle intersecting family. Okay, we need to define what is triangle intersecting family. So a family of graphs is triangle intersecting. A family of graph, let's say labeled, so over some set, common set of vertex at n, first n integer. We call them triangle intersecting if every pair of graphs from this family, they share a triangle in common. Now what we cared about is what's the largest size for a triangle intersecting family? That's what we cared about. What will be a trivial lower bound? Well, from Erdős-Corrado, we know if you have a family that's intersecting, pairwise intersecting, the trivial lower bound is you take an element and say that every set has to contain this element. So n minus 1 choose k minus 1. Sorry, this is non-uniform setting. So it's 2 to the n minus 1. Everything should contain this element, right? And naturally, we want to do the same here. If we require every pair of graphs to have a triangle in common, why don't we just fix a triangle? Let's say triangle 1, 2, 3 is our triangle. And you take all the graphs that are super graphs of this triangle 1, 2, 3. So all the graphs containing one same triangle. So taking all super graphs, just taking all graphs containing a fixed triangle will give us a lower bound, which is at least we have n choose 2 possible edges to take. We fix 3 of them, which is coming from this fixed triangle. For the remaining edges, you do whatever you want. That's a number of supergraphs containing this triangle. And this family, for sure, is triangle intersecting. It is now known that this lower bound is optimal. This is a result about 15 years ago, about 10 years ago by Alice Filmus and Freischgott. Today, we're going to prove a slightly weaker upper bound within a factor of 2 height. So Alice Filmus Freischgott showed that matching upper bound. Here we're going to prove something slightly weaker, a factor of 2 apart. So we're going to prove theorem, a triangle intersecting family F on the common vertex at n has size at most 2 to the n choose 2 minus 2. So we just one off in an exponent, a factor of 2 apart. How do we prove this? Well, again, Schur's lemma in a slightly clever way. Well, the first step is trivial. We want to give an upper bound on the cardinality of F, this triangle intersecting family. What we're going to do is we're going to uniform random sample an element from this family. So we sample a graph from F. This will be a random graph. Proof. Sample this random variable to be a graph. random element from F. So what do we know? We know that entropy of this is log of the cardinality of F. And our goal is to prove, after taking log, this is at most n choose 2 minus 2. To apply Schur's lemma, we need to view the random variable x as in a vector form, right? And then we take a random subset of the indices of coordinates. Here, it's not what indices, what vector form we should take. It shouldn't be over the vertices coordinates, because look, this is product space over pairs of edges we're going to take. So the vectors, this vector x, if you view it as a vector, it should be over pairs of vertices. So we're going to view x as a vector xe. E is all possible pairs that could be an edge. So this is the indicator function for E is an edge in X, where xe is the indicator function for the events E in X. All right, good. All right, so we are now in the position to apply Schur's lemma. The Schur's lemma says, okay, we need to sample a subset of the coordinates. Here, the coordinates are pairs, so pairs in N. So we need to sample a random subset of this guy, which is basically like a random graph, right? So now, what's the natural choice? Well, the choice we're going to make is we're going to take union of two cliques. Okay, here's our choice. This is the clever bit. So now we are consider uniform random subsets R in N. So R is a uniform random subset of N. Here's a picture. This is R, and this is complement of R. And our random subset of indices will be the clique it will be the union of two cliques, one on R, one on its complement. And let G be the random graph consisting of two cliques, one on R, one on complement of R. So this is my G. Here's the picture. Okay, G is the F in the Schur's lemma. Now we're going to estimate, okay, first of all, what's the probability? We need to estimate each coordinate, which is each E in here, has decent probability to appear in G. That's easy. Well, since R is uniformly chosen, as R is uniformly chosen over a subset of R of N. It's easy. I left the exercise to show that for every pair, the probability that E lies in G in this index set is, this is our mu in Schur's lemma, is 1/2, probably 1/2. Intuitively, when uniformly random choose R has size roughly half of the vertices, then the probability that it lies in one of these clique is also half. Okay. Now, we can then apply Schur's lemma. Schur's lemma implies that the entropy of X is at most, so X is this vector, and our F is the G here, which is a random subset of this guy, random subset of coordinates, is at most 1 over mu, which is 2, times expectation over this random subset of coordinates, which is the random graph G, H of X projected on G. Now, what is X projected on G? Let's wait for a moment. What is this guy? Well, this is nothing but, let's write it slowly. This is XE, E in G. E is, as long as E lies in this 2 clique, is an edge in G, we consider it in XG. And X itself, uniformly chosen from this familial graph, is also a graph. We can think of X as a graph. So this is nothing but the intersection of these 2 graphs, right? You can think of it as this is X intersect G. Okay, just these 2 graphs. Good. Now we're going to give an upper bound on this right-hand side. X, we need to look at what is this, how to estimate this. Note that XG is basically the intersection of graphs if you view X and G as graphs X and G. Okay. One key observation is that when you take X is uniformly chosen from F, when you take all different F, X, these form an independent intersecting family. So key observation is that the family F restricted on G is an intersecting family. Okay. Why? Look here. We know that if you take 2 different graphs from X and X prime in F, we know that they share a triangle. If you take X and X prime, we know they share some triangle. The triangle looks something like this, right? X, X prime in F, then X intersect X prime has a triangle in there. So the triangles look something like this. And what is this guy here? This edge is precisely X prime G, right? This implies X prime intersect G and x double prime intersect G is non-empty. So restricted on G, the family F is an intersecting family. But restricted on G, that's where this random variable is taking value from. This implies, and first of all, this restricted on G, this family is an intersecting family. That means this restriction on G has size 2 to the E of G minus 1, because when you restrict it on G, the number of the ground set has size exactly E to the G, the E of G. So when you have a ground set of size E of G, take an intersecting subset of this is 2 to the this guy minus 1. Okay? So we have as xg takes values over f restricted on G by maximality, it implies that no matter what G we take, this is at most h of xg for any G is at most no, for this particular G, sorry, is at most log of this guy. Okay. All right. So we have plugging in here, hx is at most 2 times expectation over G, E of G minus 1. Okay. But what is expectation of the size of G? Remember, every edge E lies in G with probability 1/2. So the expectation of size of G is 1/2 times n choose 2. So this is 2, 1/2 times n choose 2 minus 1, n choose 2 minus 2, as we want. Right. That's what I want to cover today. Any question? The next time we're going to see more applications in graphs and in some other discrete structures. All the rest of the lectures on entropy will be applications. All right, if there's no question, we're going to resume on Thursday, same time. See you guys then.